Gases, Part 4, the ideal gas law. You're going to learn in this video how to predict the pressure, volume, temperature, or the amount of a gas. Have you stopped to consider that in all of the gas laws we've looked at so far, there has been one gas property that we haven't changed at all? Do you know what that property is? It's the amount of gas. Everything we've said so far has been for a fixed amount of gas. Well, that all changes today. The ideal gas law will allow us to relate the amount of particles, which is not something you can observe directly, with the pressure, volume, and temperature of a gas. The ideal gas law states that the number of gas particles is directly proportional to the pressure and volume of the gas, but inversely proportional to the Kelvin temperature. When we write it as an equation, we'll use pressure times volume equals number of moles times the universal gas constant times the Kelvin temperature. That's PV equals nRT, where the lowercase n is the number of moles and capital R is the universal gas constant. To deal with the units, we will use one of these three universal gas constants. You'll want to write these down somewhere convenient. R is equal to 0.0821 liters times atmospheres divided by moles in Kelvin, but it is also equal to 8.31 liters times kilopascals divided by moles in Kelvin. It is equal to 62.4 liters times millimeters of mercury divided by moles and Kelvin. Which R you use depends on which pressure unit you use in your calculation. Just make sure it agrees. Additionally, you'll need to use liters, and only liters, for the volume, moles, obviously, for the moles, and Kelvin, of course, for the temperature. Here's our first look at an ideal gas law problem. What is the Celsius temperature of 24.9 grams of oxygen in a 1.5 liter vessel at a pressure of 143 kilopascals? Pause the video here so you can work this one out for yourself. To solve this problem, we're going to need to find T from PV equals nRT. We've got V in liters, so that's good to go. We've got pressure in kilopascals, so that's good to go as long as we use the correct R value of 8.31 liters kilopascals over mole Kelvin. But the oxygen gas is in grams, so we've got to use molar mass to convert the 24.9 grams of oxygen into 0.778 moles of oxygen. Now we're ready to solve for T and substitute P, V, N, and R. So we get T equal to 143 kilopascals times 1.50 liters divided by 0.778 moles and 8.31 liters kilopascals over mole Kelvin. If we put the numbers correctly into our calculator, we'll get 33.2 Kelvin, rounded to three significant figures. The problem wants the answer in Celsius, so by subtracting 273.15 and rounding correctly, we'll get negative 239.8 degrees Celsius. How about one more ideal gas law problem? How many moles of carbon dioxide gas are present in a volume of 250 centimeters cubed at standard temperature and pressure? Pause the video so you can work this one out for yourself, y'all. Now let's work on it together. To answer how many moles of gas there are, we'll need to solve for N in the equation. But thinking ahead, I'm going to convert 250 cubic centimeters into liters. Since milliliters is the same thing as cubic centimeters, we'll just need to move the decimal 3 places to the left and get 0.25 liters for the gas's volume. Anyways, back to the ideal gas law, PV equals nRT. So N is equal to PV over RT. If we substitute in everything we know, we'll do 1 atmospheres for P times 0.25 liters for V divided by 0.0821 liter atmospheres per mole Kelvin for R, and also divided by 273 Kelvin for T. That means there would be 0.011 moles of carbon dioxide at this pressure, volume, and temperature. Pow! I hope that you've been able to predict the pressure, volume, temperature, or amount of gas based on this video. If not, then just ask for help. Thanks again for watching. I'm out.